A central metal atom, if it is bonded with ligand, get hybridized, it will form a new complex. The hybridization scheme is showing of electronic configuration of cobalt atom is 3d7 4s2. Due to the unpaired electrons, it will form paramagnetic in nature and it is having tetrahedral geometry. Linkage isomerism is a type of isomerism in which two complex compounds differ in the donor atoms of ligands. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Now I am going to start session 2 from the chapter Coordination Compounds. In the previous session we have discussed about classification of inorganic salts, definitions of terms related to coordination compounds, coordination sphere, coordination polyhedron, oxidation number of central atom and nomenclature of coordination compounds. These are the concepts which we have already discussed in the previous session. In current session we will discuss about isomerism in coordination compounds, Varna's theory of coordination compound, limitations of Varna's theory, valence bond theory which will be called it as VBT, applications of VBT. Okay. Isomerism in coordination compounds. Usually isomerism means the compounds which have same molecular formula but difference in structural formula or orientation of compounds, or usually structural formula will be different. That kind of phenomena will call it as isomerism. Okay. Isomerism are mainly classified as stereoisomerism and structural isomerism. That stereoisomerism further divided into geometrical and optical isomerism. Here structural isomerism are further divided into linkage, coordination, ionization and solvate isomerism. Okay. Isomers are two or more compounds that have same chemical formula but a different arrangement of atoms. Because of the different arrangement of atoms, they differ in one or more physical and chemical properties. They are of two types. As I told, isomers are two or more compounds having same chemical formula but different in structural formula. Those will call it as isomers, and they are classified into stereoisomerism and structural isomerism. Stereoisomers have the same chemical formula and the chemical bonds but they have different spatial arrangement. It is further classified as geometrical and optical isomerism. In this stereoisomerism, chemical formula will be different but arrangement of bonds will be different. In structural isomerism, chemical formula will be different but different chemical bonds will be seen. So it is further divided into linkage, coordination, ionization and solvate isomerism. Next, geometrical isomerism. It is a phenomenon in which two complex compounds have the same molecular formula and the same chemical bonds but different geometrical arrangement of the ligands. The two forms are called cis and trans forms, generally found with compounds having coordination number 4 and 6. Okay. If you see here, molecular numbers are same, bonds are also same but different in spatial arrangement of those bonds. If ligands are in same side, that is cis. If the ligands are in opposite side, that they will be in transposition in square planar complex. But in octahedral complex, you can observe here at the adjacent side ligands will be attached, so it will be called it as cis. At the opposite side ligands will be attached, that will be called it as trans. And this is one more example for octahedral complex showing stereoisomerism in which geometrical isomers can be exhibited. Octahedral complexes of type Ma3B3 exhibit another type of geometrical isomerism, that is facial isomer or meridional isomers. In here you can observe ligands are at adjacent side but here ligands are at opposite side. In facial isomerism, ligands, three donor atoms of the same ligands occupy adjacent side. All the three donor atoms are at adjacent side but here in the opposite side in meridional isomer. This is the another type of geometrical isomerism exhibited by octahedral complex. Next, optical isomerism. It is a phenomenon in which two complex compounds have the same molecular formula and the same chemical bonds but cannot be superposed on one another. See here, in optical isomerism, having same molecular formula, same bonds, everything, but in the mirror images cannot be superimposed on one another. So, it is dextro and it is levo isomers. Okay, they differ in rotation of plane polarized light. These isomers are called enantiomers. The two forms are called dextro and levo. The plane polarized light rotation will be different here, but same molecular formula, same bonds, everything will be same other than rotation of plane polarized light. If it is right rotation, dextro; if it is left rotation, levo. Optical isomerism is common in octahedral complexes involving didentate ligands. Example, D and L isomer of cobalt ethane 1,2 isomer of cobalt complex. Only cis isomer shows optical activity. Okay, only cis isomer can show optical activity. Next, structural isomerism. Structural isomers, the same chemical formula but they have different bonds. Types of structural isomers, in that linkage, coordination we'll discuss now. Linkage isomerism is a type of isomerism in which two complex compounds differ in the donor atoms of ligands. It is shown by complex compounds containing ambidentate ligand. See here, linkage isomerism is a type of isomerism in which two complex compounds are different in donor atoms. See here, it is having the same molecular formula, but here ambidentate ligand will be attached to the metal atom in one ligand, one complex, and another complex it will be ambidentate ligand will be attached through another donor atom. We'll call it as linkage isomerism. Next, coordination isomerism. Coordination isomerism is type of isomerism due to interchange of ligands between cationic and anionic entities of different metal ions present in a complex. See here, metals will be interchanged here, cobalt with cyanide and chromium with amino. Okay, that is called coordination isomers where anionic and cationic entities will be different. Next, ionization isomerism. Ionization isomerism is a type of isomerism in which two complex compounds produce different ions in solution state. Here, when it has been dissolved or ionized, it will get ionized with different ions in solution state. It will give different ions and that complex will give different ions. Solvate isomerism. Solvate isomerism is a type of isomerism in which complex compounds differ in the number of water molecules acting as ligands and water of hydration. Okay, here the number of water molecules acting as ligands and water of hydration will be different. This is also known as hydrate isomerism when water is involved as a solvent. Here it will act as ligand, here it will act as solvent. And that is about the classification of isomerism in coordination complex. Next we will discuss about Varna's theory of coordination compounds. The main postulates are central metal atom or ion show two types of valencies, that is primary valency and secondary valency. The primary valencies are ionizable and are satisfied by negative ions. Primary valency will be ionizable and satisfied with negative ions. The secondary valency is non-ionizable and it is equal to the coordination number of the central metal ion. It is fixed for a metal. Secondary valencies are satisfied by negative ions or neutral molecules. And the primary valency is non-directional. The secondary valency is directional. Ions or molecules attached to satisfy secondary valencies have characteristic spatial arrangements. Secondary valency decides geometry of the complex compound. See here example. This is one complex. Primary valency is +3. Secondary valency is 6, which is a coordination number. Okay. Primary valency is exhibited by 6 because ammonia ligand has been present, and secondary valency is exhibited by 3Cl ligand. Geometry is overall octahedral geometry. Okay, and we have told it is ionizable and replaced by negative ions. That's why primary valency will get replaced by neutral ligand. And this theory will fails to explain A few elements have the property to form coordination compounds. The bonds in coordination compounds have directional properties. We know that some of them are, the primary valences are non-directional. Due to the directional properties are in coordination compounds, the Varna's theory will fails to explain this. Coordination compounds have characteristic magnetic and optical properties. Due to that properties of coordination compounds, Varna's theory will not going to explain. So these are the limitations, and those theory will not support the coordination compounds who's having these properties. Next, valence bond theory. The metal atom or ion under the influence of ligands can use its N-1d or NS-Np or NS-Np and orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar and so on. These hybridized orbitals are allowed to overlap with ligand orbitals that donate electron pairs for bonding. A central metal atom, if it is bonded with ligand, get hybridized, it will form a new complex. It is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior on the basis of the valence bond theory. If the coordination number is 4, type of hybridization is sp3 and it can be tetrahedral structure. If it is 4 and it can be dsp2 and square planar can be its shape. 5, sp3d trigonal bipyramidal. If it is 6, sp3d2 octahedral, and again if it is 6, type of hybridization may be changed into d2sp3. The structure will be octahedral only. We'll see now example one by one. In octahedral complex with having low spin or spin paired complexes, okay, in cobalt this complex, oxidation state of cobalt ion is in +3 oxidation state and has the electronic configuration of 3d6. And the hybridization scheme is showing of electronic configuration of cobalt atom as 3d7 4s2. 3 means the electron should be removed. So remaining 6 1 2 3 4 5 6. Okay, it will get hybridized and it will form d2sp3 hybridization. Okay, the geometry will be octahedral and due to no unpaired electrons are present in the shell, it will form diamagnetic in nature. It will not show the magnetic property at all. It is having the diamagnetic nature due to the absence of unpaired electrons in the shell. Next, high spin. In the high spin complex, hexafluorocobaltate, oxidation state of cobalt is +3 in this also, and electronic configuration 3d6, and here also 3 electrons will be not there, and regarding 6 electrons it will get not merged due to the high spin. That's why 4 unpaired electrons can be present and sp3d2 will be formed. Here the magnetic property is paramagnetic. Whenever the low spin was there, it get merged, it get hybridized, but here it will not get hybridized, okay, due to the high spin complex, and the geometry is octahedral and the magnetic property is paramagnetic. In tetrahedral complex, nickel tetrachloride, oxidation state of nickel is +2 and it is having electronic configuration 3d8 4s2, and nickel 2 plus means 4s2 will be removed and it is having 3d8. 2 unpaired electrons will be present, okay, it will form sp3 hybridization. Due to the unpaired electrons, it will form paramagnetic in nature and it is having tetrahedral geometry. Next, square planar complex, that is nickel tetracyanate, nickel having oxidation number of +2, it having electronic configuration of 3d8. Nickel 2 plus means 2 electrons will be removed, it is in low spin, so all the electrons will get hybridized, no unpaired electrons only present, so it is having dsp2, so dsp2 hybridization. Due to absence of unpaired electrons, it will show diamagnetic in nature and it is square planar geometry. This is about the overall isomerism and Varna's theory, also valence bond theory of coordination complexes. Next session will discuss about magnetic properties of coordination compounds. I hope you have understood completely whatever I have taught in this session. We'll meet in the upcoming session. Thank you.